I will tell a few words then about François Hild, then Anil Misa will talk about J and Reddy. I know prizes are a delicate issue. The committee can be wrong. However, you know, we are scientists. We're not earning huge amount of money. We are not dominating the world. We are not changing the policy of big nations. The effect of our work will be seen after many centuries. For instance, I think that Europe became great, Western civilization became great because of Achilles. But he died many, many years before the effect of his ideas were effective. So why people should spend their life in science? At least we give them some prize. Okay? So I think this is a strong motivation, and I must thank Yves when working together with me. He was responsible of CNRS, and I was organizing for M&MoCS many common activities when he pushed me to organize this project. Then I will say a few words about the fact that this is a rather young prize, but you know, I'm sure that even for better prizes, the two recipients belong to the best category of prize winners. You know, there are two prize winners kinds. One winner, one kind of winners is honored by the prize. Another kind of winners honors the prize. They both belong, in my opinion, to this prize. So I am very happy to start reading the short laudatio which I prepared for François.
Short. Je connais trop.
And tonight, during the dinner, we present them a pergamena, a parchment with the statement of the prize. I'm very sorry, I tell everybody now, we will be like Cinderella. There is a strange bureaucrat who blocked with an alarm this building at midnight. I spent the whole day trying to postpone this later, and it is impossible. You know, it is always fault of a problem. Okay? Insurance, fire, this kind of thing. So now on we run. Please arrive 8:50. Because 8:30 we start eating. Okay? There will be some nice music, and 11:20 I will give the parchments to the winner. Okay? German schedule. Okay. By the way, yesterday we had a small trial dinner here, and some fuses allowed us to eat in the darkness. Maybe. We did everything. Let's cross the fingers. It should work. Okay. Now, I become sick. François Hild, CNRS research professor at the Laboratoire de Mécanique et Technologie, LMT, École Normale Supérieure Paris-Saclay, was a former student of this institution in mechanical engineering, holder of a PhD from the University Paris-Saclay and from University of California at Santa Barbara. François Hild conducted most of his research at LMT. Recently, he was awarded by CNRS 2017 silver medal for all his work in mechanics of materials and structures. He started with a research in brittle fracture, so he tried to give a unified framework for data structure. He completely renewed the classical approach to make the ingredients of the underlying statistical theory bear fruit within a thermodynamical base and considerably broader mechanical framework. Thus, damage in composite material, fatigue of materials, or dynamic fragmentation are areas where the unified framework was expressed, allowing a link to be made between the microscopic and macroscopic scales in application fields driven by the statistics of extreme rather than by average mean. But in my opinion, his bigger contribution are in pioneering of image correlations. We can talk about second period of like Picasso. A second period of François Hild's work in close collaboration with Stéphane Roux concerns the revolution in experimental mechanics through image-based full-field measurements. In the correlation of digital images, original approaches were developed that use modeling tools to analyze mechanical tests. The way of performing measurements in the test was renewed. Then the tests themselves, by making an increasingly close link with the control of the test, with the description, card, and final element of the studied part, with their numerical modeling, or with the identification of mechanical properties. At the same time, the notion of image has also flourished tremendously in different modalities, at different scales, in the third dimension via tomography, and in the fourth dimension via time series. Okay, he has many patents, he wrote many articles, he has a high H index, he worked with industries as only French scientists can do. But I wanted to be sure to read some of the series, but I will conclude. Then we will hear François telling you that, as usual, when I work in France, and in particular, when I started working with François, I discovered that French school really is one of the best in the world. An experimental mechanician knows calculus of magnitudes. You can talk about abstract mathematics and he corrects you. Even if he can do measurements. I think that this is the key of future development of our science. Okay? So I think that for this reason the committee agreed to give him the prize. So thanks.
Thank you. Okay, thank you, Francesco. Thanks for the invitation and for the laudatio. So when Francesco told me that I was supposed to give this presentation, it was last year. And last year actually marked the 10th anniversary of global digital volume correlation. And so hence the title. Before I start, I'd like to acknowledge Stéphane Roux, who is actually in the room, because actually he's the main contributor to the work I'm going to present. And also our research team, because as you know, without brilliant students, nothing would happen. Okay, so of course I will have first to introduce what we call digital volume correlation, but I won't spend much time on the technique itself, but more on various applications of the technique over the last decade. Okay, and actually, why we are using this technique? Volume here means that we are dealing with 3D images. One way of getting 3D images is via X-ray computed tomography. Namely, you have an X-ray source here, and you illuminate a sample, you have a detector, and basically you gradually rotate the detector, acquire a series of radiographs, and with these radiographs you reconstruct 3D volumes. And so this type of imaging technique is very interesting for people like myself, whose background is more on the mechanics of materials side, because basically you can image a sample without destroying it, even though you load it. And so that's typically the type of data you will want to analyze. The second reason I'm talking about that, and this has to do with the fact that the very first in situ experiments in such environments go back exactly 20 years ago. And here is a picture of one of the very first in situ testing machines. Back then it was performed in a beamline in Grenoble on the synchrotron radiation facility. But more than often now you can also have access to lab tomographs, and here is an example of a testing machine we have in our lab where you can prescribe tension, compression and torsion and image the sample in situ. Okay. Now, 2019 is also the 20th anniversary of digital volume correlation. The very first paper was published exactly 20 years ago by Brian Bay and his colleagues, and the first application field was in biomechanics and then extended to mechanics of materials. And so basically the very simple scheme is to consider two reconstructed volumes, one in the reference configuration, one in the deformed configuration, and basically you will subdivide this volume into small interrogation volumes, and you will want to determine back then what was the mean translation that occurred for this small integration volume between time 0 and time t. And so if everything were perfect, the gray levels at the voxel locations x will have moved to x plus u, and so basically what you try to do is determine u by minimizing the sum of squared differences with respect to your unknown translation. And mathematically speaking, you can actually prove that it's equivalent to maximizing the correlation product provided the volume is very large, and which means that initially what was done was to maximize this correlation product, ergo the name digital volume correlation. Okay, and as I mentioned already, an alternative to the previous technique, which basically provides you cloud of 3D points for which are the centers of all these interrogation volumes and for which you determine translations, was to introduce global registration schemes. The idea is basically identical to the previous one, but instead of considering small integration volumes, now you consider the whole picture or most of it. The fact that you consider larger volumes means that the kinematics will become more complicated, but you will also want to have more details about it. You still minimize this gray level difference, but over the region of interest. Now, if you just consider an iterative scheme, and let's say we are at an evaluation of u tilde, and you ask yourself what is the best correction to apply to it, you perform first order Taylor expansion of the integrand here. And basically what you end up with the corrections you're after and the gradient of the original image in the approximate solution, which tells you that for these techniques to work, you see that what you're looking for is these corrections, and they appear as scalar product of these image gradients. So you need some contrast in the pictures to measure displacements. And remember that we're dealing with tomography, so there is no way of applying a speckle pattern as you would do in regular DIC techniques, for instance, digital image correlation techniques. Okay, now the fact that here this is minimized over the whole region of interest will mean that we can then use more complex kinematic parametrization, and I'll explain a little bit later on this point. What is also important to note that we started with two volumes, one in the reference configuration, one in the deformed configuration, and in the minimization scheme there is a third one, which is the difference between the volume in the reference configuration and the volume in the deformed configuration corrected by the measured displacement. And so these are the so-called gray level residuals, and if everything works perfectly well, at the very end of the process you should only have acquisition noise, presumably reconstruction artifacts and things like that. And this is very important because you end up with a third volume, and this is the way of controlling that you get a meaningful result. Because this type of procedure belongs to the class of ill-posed problems, and you have to make sure that everything is correct. Okay, now, most of the time when you think of 3D imaging and tomography, this allows you to image stick-like samples, which is fine. And here is a cartoon of what you would find in synchrotron beamline. But you can also image thin sheets by basically having a rotation axis that is no longer perpendicular to the beam axis. And this is called laminography, and this is very interesting because now you can test samples that are a lot larger in the two transverse directions, provided you can still have the X-rays that traverse the material. Which means that, for instance, you can apply meaningful engineering boundary conditions to your experiment, which usually is not the case here, because depending on the material, the thickness of the samples remains reasonably small, because you still have to acquire some signal that's traversed your sample. Okay. And so this is an actual experimental setup, again in Grenoble, France, where you have a shear experiment that was performed on an aluminum alloy sample. And that's the transition to the first illustration I'd like to comment, which is to understand the so-called flat to slant transition. What do we mean? If you take a notch sample on, for instance, an aluminum alloy used in the aeronautics industry, and you basically just pull it in the mode 1, so the opening regime, what you see is that you start then having a crack that basically initiates and starts to propagate in mode 1 condition. But very early on it tilts. And this is something that is known for some time. The question is, what is the driver behind this phenomenon? And there are basically two explanations. One, which is plasticity occurs first and drives this transition, or it's damage. And in damage, of course, you would think in terms of localization, and in the fact that eventually you may have a localized band. Now, if you look at post-mortem observations of such materials, what you would see are typical of ductile damage, dimples all over the place. So in that sense, it's pretty clear you have a damage mechanism, and it's the driver. Now, the problem is that this is post-mortem, what's happening during the experiment. Now, to understand what's happening during the experiment, what was done was to image a volume close to the notch root, and then analyze this volume with digital volume correlation. And in this first example, we used regular hexahedra, a finite element mesh, and that means that our unknowns are now the nodal displacements associated with your discretization. And here is an example of one of these elements. So each voxel size was 0.7 micrometers. And in this material here, you see that there are not so many markers. At least it's less than 0.4% of volume fraction. But still, we try to use DVC. And in this particular example, you have access to something like about 60,000 degrees of freedom. Okay, and so this is now the volume in the reference configuration that was thresholded just to reveal basically all the secondary particles in the material. And then for the first loading step, here you see a 3D rendering of the equivalent strain field. And in parallel, you will see the thresholded volume again. So basically, there is nothing that is happening there in comparison with the reference configuration. Let's proceed to the second loading step. Basically, you have this X-shaped type of strain bands. I call them strain bands because, of course, you have lots of strains in the bands, but you still have also plastic strains in the bulk. And you still see a little bit of activity, but nothing correlated to the presence of these strain bands. And so, again, for the third loading step, you see a little bit more activity there in terms of damage, but again, nothing really related to these bands. And this is the final calculations that we could run, where you see one of these bands that is taking over. Again, a little bit more damage activity, but again, not correlated to these straight bands, which eventually led to fracture. Which means that in this particular case, you could clearly prove that the driver behind this phenomenon is plasticity. Okay, so that was the first example, and just to prove that this was not just one material in one given consideration, two different materials with two different heat treatments, that meant that the hardening behavior was totally different, basically led to the same type of result. Which means that this is probably more generic than what was initially thought. Okay, so this was the first use of DVC alone. So it was used as a standalone technique to analyze an experiment and then discuss deformation mechanism and then a failure mechanism. Now, as Francesco mentioned, we'd like also to bridge the gap between experiments and simulations, and the reason for that is, first of all, remember I talked about the FE mesh. So basically you measure kinematic bases that basically talk the same language as the finite element simulations, and so it's rather natural then to try to compare what you would measure with what you would simulate. And as a first example, let's consider nodular graphite cast iron. That's one of our favorite materials because the graphite nodules have absorption coefficients that are totally different from the ferritic matrix, which means that you know it's the kind of speckle pattern you would dream in 3D imaging. And here this sample was pre-cracked initially via a load shedding technique to make sure that plasticity was really confined close to the crack front. And given the fact that now we can measure displacements, and the first part of the measurement was again to use a regular mesh of cube elements. And remember, I introduced the correlation residuals, or the gray level residuals. Here you have a thresholded gray level residuals. We used standard FE mesh, therefore you assume continuity everywhere in the analyzed volume, which is actually true except where you have your crack. And so that means that thanks to these residuals now, you can construct the cracked surface and actually even use level set techniques that are used in extended finite elements. In this particular case, if you had just thresholded your picture, it would have been impossible to distinguish the cracked surface from the nodules, because in terms of gray levels, they were approximately the same magnitude. But the gray level residuals basically, as we will see later, will make the microstructure totally disappear and just reveal basically something that was not accounted for, and here it was the presence of the crack. And so then you can account for it, rerun an analysis, but this time with a kinematic basis that is exactly the one that you would use in numerical simulations, and you would enrich it with additional discontinuous contributions. And so that means that now you are able to analyze pictures for which you can reveal your cracked surface. You can measure displacements that basically obey the same hypothesis you would use in numerical simulations. From that you can extract stress intensity factors, and this extraction also allows you to construct the crack front. But you can also, in parallel, then run an XFEM calculation in which you prescribe the measured boundary conditions on the top and bottom part of this volume. And then compare, actually, the stress intensity profiles you measure experimentally and you predict numerically. And in this particular case, here is the mode 1, 2, and 3 stress intensity factors along the crack front. So we are basically traveling within the material. And the solid lines here show you the XFEM simulation results. And the symbols here are experimental evaluations. What you see is that there is a very good agreement that allows us to say that we validated these XFEM simulations. Please note that had we just prescribed uniform boundary conditions as you would expect from a perfect experiment, you would have predicted basically a constant stress intensity, mode 1 stress intensity profile, which is not the case in this particular experiment. And this has to do with the scale of the samples and the fact that the geometry and the testing machine was very compliant. Okay, so that was the first example in which you wanted to validate numerical simulations. Now, can we go further and say something about material properties? And in this first example, we were after the understanding of what was going on in plasterboard. And in plasterboard in particular, you would use nails, and so you have to make sure that it's still okay. And so one typical experiment to mimic that is to perform indentation tests. Now, in indentation tests, basically all the action is taking place under the indenture, which is something you don't have access to except if you use 3D imaging techniques. And as you will see, we were after the crushing mechanism that occurs under the indenture and possibly identify an onset criterion. Okay, and so in this experiment, here you have the load versus displacement curve of the indenture, and the fact that this curve is basically linear is an indication of a nonlinear underlying mechanism, and each letter here indicates that you are acquiring one scan. And so here now we'll see the central section of each of these scans as the applied load increases. In this particular case, the experiments were performed in Lyon, the Matisse lab, so in a lab tomograph. Okay, and what you see initially is that indeed you have the beginning of an indentation, and very early on actually you have some pore collapse, because actually plaster is a brittle foam. And so as you push the indenture, here you will have this crushing mechanism that will develop, as we will see. And so as the load level increases, you see that basically it's the development of this crushing zone that is basically invading the sample as we push more and more the indenture. The material is still able to carry some load. Okay, and so what will be done now is to focus around this area and try to understand what's going on. Now, if you use standard DVC with a regular mesh, well, what we were really after understanding what was going on between the undamaged material, pristine material, and the crushed material, which means that you would like to have a very fine discretization. But if you take a very fine discretization, and here in this particular case it was elements of edge size 8 voxels, that means that the measurement uncertainty is on the order of 0.4 voxel, which means that there is no way you can measure reliably elastic strains. But we would still want to have a very good description of this front. Now note also that because we have this crushing zone, the residuals, they tell us where the calculation didn't work, and basically it was in the crush zone because we don't have conservation of gray levels because we have this pro-collapse. So in that sense, DVC is doing its job, but still it's difficult to extract some meaningful information. So the idea then was to say, okay, if we can perform an analysis away from the crushed zone, basically the behavior is elastic. So we are going to use numerical simulations to basically measure fields. By that I mean that we will reparameterize our DVC problem in an area where we can make some assumptions on the material behavior. Of course, most of the crushed zone has to be excluded because in that part this hypothesis will not be correct. And so that means that basically here what we will do is prescribe on the bottom part what was measured with standard DVC. And this will be rigid body motions, and will determine here the boundary conditions in terms of a few kinematic parameters that allow us to get the best match with the experiment. Best match meaning that we will control that with the gray level residuals. And so that means that we can now come up with a reduced kinematic basis that is constructed with numerical simulations that are totally consistent with the experiment, at least at the bottom part, because we prescribe the measure boundary conditions, and for the top part, well, we determine these Dirichlet boundary conditions with very few amplitudes. What turned out to be important is obviously the dominant mode, which is the one that we would expect with indentation, but also two transverse modes that again are due to the fact that the experiment was not perfect. And these two modes turned out to be critical to really minimize the gray level residuals. Okay, and so here is just again a 3D rendering of the gray level residuals for different applied load levels, and you see that basically the crushing zone develops. In the crushing zone, of course, no way you can measure meaningful results, but what is more important to note is that we don't see any deviation outside this crushing zone, which indicates that the reduced basis is consistent with your experimental data. Okay, and so from a static analysis of the problem, it suggested that we should look for an onset criterion based on a ranking stress, this time the smallest so the minimum principal stress. And so here is a 3D rendering of this stress. And so now the question will be, for different stress contours, which one matches best the transition between the pristine and the crushed zone. And so here is the comparison between the residuals on the green ones, and the red one is this stress contour for minus 5 megapascal level, minus 6, and minus 7. And so basically in this type of setting, it turns out that the best agreement was given by minus 6 megapascal, which means that you have a way of not only proposing a criterion but also validating with experiments. Okay, so that was for constructing a criterion for crushing of plaster. And now I will move on to an example where we are basically trying to do exactly the same but at the micro scale. Up to now, you may argue that, okay, that's fine, but you performed macroscopic type of calculations. Can we do the same type of exercise at the micro scale? And so let's go back to cast iron, for instance, and here again is an example of the central part of a cast iron specimen that was imaged now in our tomograph in Cachan. And so these were the original data that we had for different load levels. Now I hope it's clear that given the fact that we have different reconstructed volumes, we can measure displacement fields and check for their trustworthiness in terms of experiments. And here you have an ortho slice of the gray level residuals. Unfortunately, probably none of you will see that they're basically, for you probably it's black everywhere. Actually, it's not exactly the case, as we will see, around the nodule to matrix interfaces. I'll come back to that a little bit later. Actually, I anticipated this problem. Okay, so just to illustrate what I'm talking about, so this is a section of the volume in the reference configuration, in the deformed configuration, and here you see that you had some debonding that occurred. Remember, that's what we saw, or what you have to trust me, that's what's seen in the residuals. That's the raw difference that you do with the two volumes, so you didn't correct for any kinematic quantity, and that's at the end of the registration process. You see that basically the microstructure disappeared except around the interfaces I was talking about. And in particular, you see some areas clearly that are indications of debonding. And this debonding took place very early on in the experiment. Okay, now we have the volume in the reference configuration. You can also then come up with procedures that would construct meshes that are totally consistent with this particular experiment, namely to basically tailor your mesh to your volume of interest. And to make a long story short, and this is a collaboration with my colleagues from CEMEF, close to Nice in France. They used an immersed mesh technique based on level set functions again, and to construct meshes that are consistent with the underlying microstructure. And so this is the example on the sample we were studying. So here you see two meshes. The red one, which is the one that is consistent with your microstructure, and the blue one that was actually used for DVC calculations. The fact that we have here a mesh that is repositioned in these volumes allows you now to compute the response of this volume by prescribing the measured boundary conditions. Which means that now you have a simulation that is consistent with the underlying microstructure and the boundary conditions. And so that means in this particular case, what was done was to assume that the nodules were basically elastic and the ferritic matrix was elastoplastic with Ludwig's law. So very simple law. Anyway, the fact that these simulations were driven by measured boundary conditions allows you then to also compute the gray level residuals independently from the previous case, which means that this allows you to compare the performance of this procedure in comparison with the direct procedure where you only use DVC. And remember that the mesh is a lot finer in the numerical simulations. Okay, and so to decide which one is best, we'll turn to the residuals again. And so this was the section I already showed you for DVC alone. And now this is the section for the FE simulation at the microscale driven by measured boundary conditions. Obviously the two are not identical, but they're it's mostly around the nodules that there are some significant differences. Okay, which means now that we can compare individually the merit of this first approach, which is purely experimental, I would say, and another one which is a combination of numerical and experimental data. And so in this particular case, now you have the gray level residuals normalized by the baseline level, which is here 1, which tells you that something is going on as a function of the scan number. And here you see the pure DVC result, and on the top of it here, the numerical simulations. So even though the mesh was something like 30 times finer than the experimental one, it's still performing poorly in comparison with standard experimental information. Why that? Because the underlying model is not perfect and is not describing exactly what's going on. Okay, so what I've introduced basically is a numerical validation framework. You may even call it invalidation in this present case at the microscale. And you see that this is now possible thanks to these 3D imaging techniques. Now, of course, you may say, hey, wait a second. Now we have a constitutive equation. Could you please update this constitutive equation and get the best parameters? Indeed, it's possible. And in this particular case, it was performed via what we call integrated DVC, namely the fact that the gray level residuals are still considered in the registration scheme that now will explicitly depend on your material parameters. And so in this setting, you determine directly the material parameters in such schemes. And here is the result for the stress-strain response of the ferritic matrix. So the initial guess that was basically obtained from literature data and the final result, which shows you that most of it, so most of the difference comes in, no surprise, in plasticity. But still you see that we still won't be able to predict what's going on here, and what was going on here was coalescence. But that's another story. Okay. It's time for me to conclude. I hope I've convinced you that digital volume correlation as introduced is operational and reliable. It's a way of dealing with 3D imaging data. And in these data, the fact that we have more than a pair of them means that we are entering the so-called 4D experiments. I've shown you some examples in which we use the technique as standalone, but you can also then bridge the gap with simulations and use validation or even calibration frameworks in an integrated way. What was also shown these last years was that initially, when this technique was introduced, so in the very late 90s, it was believed that its domain of application was really confined to materials with large contrast. Now, biomaterials are indeed very interesting for that, but it turned out that more and more materials could actually be analyzed with this technique, even though contrast was not necessarily great, and I've shown you one example of that. Good news for these techniques also is that at the beginning, either it was used in medical scanners where you had these reconstructed volumes, or in synchrotron beamlines. As you know probably, the access to these beamlines is not that easy, but more than often now you can also find labs that have tomographs, and so that means that these techniques clearly will experience a large amount of democratization. Now, of course, not everything is solved yet. What I've illustrated are only results with X-ray beamlines, but you can also use other type of modality and try to combine them. And this is in particular the case in synchrotron beamlines, where you can, for instance, combine X-ray and neutron imaging results. I just mentioned that at a given point, what is really critical in these techniques is to perform uncertainty quantifications. They are clearly higher than what we know in classical DIC techniques, but they are not too high, which means that we can still get meaningful data from these analyses. But clearly, that means that you have to be cautious and perform these uncertainty quantifications on a regular basis. One thing I didn't mention yet was the following. Remember, we talked about the principle of tomography. You acquire a set of 1,000 radiographs. The duration usually is, in lab tomographs, typically from a few tens of minutes to an hour and more. Now, during this acquisition time, you have to make sure that basically nothing moves, right? Because if something moved, that means that you would have some blur. And in the worst case, you wouldn't even be able to reconstruct your volumes. And so this means also that some type of behavior appears to be beyond the scope, namely any time-dependent behavior. To think of viscoplasticity or creep or viscoelasticity, you name it, appear to be beyond this type of setup. Now, there are some techniques to speed up the acquisition, and this is possible in synchrotron beamline because you have very energetic beams. But in lab tomographs, that's probably not the case. But hey, wait a second, we are measuring displacements with DVC, right? So if you were to be able to combine the reconstruction and kinematic measurements, that means that you would be able then to basically acquire on-the-fly radiographs and then perform a full 4D analysis to extract your kinematic basis or material parameters. Now, if you are interested in this area, Stéphane Roux will make a presentation tomorrow morning about precisely this type of technique. This type of technique is very interesting because that means that you are now able to image your sample as you would do on a regular basis on a classical testing machine in this framework. And finally, I couldn't avoid mentioning metamaterials, and in particular pantographs. Well, first of all, because of the chairman's background, but also because this is an example actually of a pantograph that was tomographed in Cachan. And one critical element of these metamaterials are what my Italian colleagues call pivots. I'm not sure I would call them pivots, but that's another debate, or call them hinges or whatever. But what really dictates the behavior of these materials are the details of this, what's going on at this level. Of course, the question now is, do you have enough pattern to run DVC? I don't know, to be tested. That's the future. And so, just to conclude, if you are interested in this subject, you will find more examples and more information about the current challenges in this review paper that was published last year. And now I thank you for your attention and leave you with Antoine de Saint-Exupéry. Thank you.
Thanks for your very clear presentation. Are there questions? Maybe one.
Dear François, thank you very much for your presentation. I just wanted to have an information with your understanding. What is the best scale to have this type of equipment? Is it the scale of the lab, the scale of different labs, the scale of the country, the scale of continent, the scale of the world, in order to have an equipment which can be available for everybody?
Okay. Good news, Yves. The type of equipment I was talking about is, well, we don't see it exactly, but you see here part of the chamber of this equipment is something that costs less than a scanning electron microscope, which means that it's affordable by a lab or a group of labs. Now, of course, the synchrotron facilities, well, as you know, that's more on a country level or even on a continent level. So for synchrotrons, clearly we won't have many new ones. But for labs, I would argue that nowadays it's, as I mentioned in the conclusion, it becomes affordable. And so I would say that if it's not for one lab, at least it's for a cluster of labs, but could be rather local.
I was wondering whether the technique can be applied to very, very soft materials, like biological materials.
Okay. Yes. Actually, the very first applications were on biomaterials. And well, actually, they weren't that soft because it was more bones and such type of materials. I guess you mean even more deformable materials. Yes. Now, in that case, I talked only about tomography, but you have other imaging means that can image, for instance, soft materials, and then there is no reason for not applying it, provided you can use the recent tricks, because the soft materials usually, that means also time-dependent behavior, which means that you would have to have fast imaging techniques. But apart from that, there is no reason why it shouldn't be applicable.
Especially the tissue, if tissue also contains fluid.
Contains?
Contains some fluidic material.
Ah, okay.
Right?
Yes.
Because that's what it is, live tissue.
Yes.
Not dry.
Yeah. Sure, and you could also have mentioned, for instance, porous materials where you had some water or something like that. And there are already some examples using either X-ray tomography or neutron tomography, which allows you then to image even some fronts, and you can do some quantitative analysis on that.
So François, congratulations for the presentation. And my question is the following. At the beginning of tomography, there was medicine and healthcare. Do you think that in the future, digital volume correlation will find application also in real-time surgery or
yes, or even when you image, some heartbeats or whatever. Indeed, and for that you have to freeze basically the motion. That's one way of doing it, and there are very nice tricks. Or you measure and you evaluate the motion and you image the technique. So I'm pretty convinced that, in particular, what I mentioned about 4D tests could be applied in particular in the domain you just mentioned. Yes.
Thank you very much for this nice talk. So I've got a question because you mentioned both DBC and the experiment
Yes.
with very special basis functions. Now, in the DBC, when you construct the displacement field, you need some set of basis functions. Would it be possible to use enriched basis functions, such as in experiment, for constructing a displacement field which has sharp jumps?
Look at the top of the...
All right, now I understood this.
Maybe I wasn't clear enough, and I apologize for that. But this is a displacement field that was measured by XDVC, where you have the discontinuous enrichment a la XFEM. And so here you basically are exactly in the same framework as what you would be in with XFEM. Okay. The only thing that was not done, as you know, you have the Heaviside type of enrichment, and then you have also the crack tip type of enrichment. DVC is not resolved enough to add these additional degrees of freedom, which means that you have, well, actually even in XFEM you have additional extraction techniques then to evaluate stress intensity factors and things like that. And actually what was done here was to develop special extraction techniques to evaluate not only the stress intensity factors but also the crack front location, and use exactly the same technique at the numerical level. That's, to my knowledge, one of the first time where some extraction technique initially developed for experimental analysis was also done numerically. Usually it's obviously it's the other way around. But here, because of the fact that it's very difficult to resolve very small displacements close to the crack front, we had to come up with such techniques. But to go back to your question, this displacement field is discontinuous, according to an XFEM type of description.
You use the elastic model in numerical calculations, but for model the best materials are some brittle materials, is cold, but elastic model not always describe good such kind of materials. Did you try some another model?
Yes. So indeed, even I didn't show, we had another experiment in which we did exactly the same type of analysis, but it was done for a larger load level, which meant that you had a yielding that basically extended a little bit more than in this particular case. And actually you could then see that something was wrong, and something was wrong in the sense that the agreement I've shown here was no longer the case, and you had an offset between numerical predictions and the experimental analysis, which was exactly what you're mentioning, the fact that you have plasticity that may no longer be in a small scale yielding configuration. Now, just one other comment. In this case where I described the behavior of cast iron at the micro scale, well then the behavior was not elastic, it was elastoplastic, and I even showed you the stress-strain response of the material. And the interesting thing is that thanks to tomography you can basically reach strain levels that are very high and that you wouldn't be able to measure from a more macroscopic point of view. So yes, this is indeed possible, but that's the very beginning in DVC to account for nonlinear models, because there is one point I forgot to mention, and I should, is that it's very nice, these integrated frameworks, but what I described in this talk took us 15 days, because each calculation is few hours, which means that nowadays, with the type of data that we have access to, one big challenge is to process all these data in a reasonable amount of time. And the meshes are quite evolved. The fact that you have non-linearities makes the calculations longer. But that's the future anyway.
Thank you. And one comment. You try to use the method with some materials that are purely well described by elastic model before. Because brittle materials are they can damage well, and the elastic model gives I'm very impressed because you get such good the similar results between numerical prediction and experiments. It's incredible for me. And what about some pure elastic materials? We will work with some wood or alloys and did you verify the statement with this material?
Well, not yet, but just I may argue that plaster is an interesting material because it's essentially elastic, as you mentioned, but you have also this crushing mechanism. And so you had to understand the transition between elasticity and a nonlinear material that is even softening in a sense, but thanks to the fact that indentation basically stabilizes everything, you can at least start constructing part of the constitutive model. But you know, we are just at the beginning of these techniques. There are not so many cases in the literature where you try to do this type of procedures. But hopefully, in a matter of few years, it'll increase rapidly because, as I mentioned, more and more people have access to these data, and there are very nice models around, and they basically are ready to be probed.
Thank you. It's obvious that it's got a big potential. Big potential.
Yep. Thanks.
Okay.